All right, in this section, we'll be applying what we learned about vectors to look at more real-life examples about the equilibrium of a particle and the equations of equilibrium, and free body diagrams to make sure that you've got all the forces in there and everything like that. So for the condition for the equilibrium of a particle, all right, a particle is said to be at equilibrium if it remains at rest, if originally at rest, or has a constant velocity if originally in motion. And so our equations for equilibrium is that the sum of the forces is equal to 0, right? Because sum of the forces is equal to mass and acceleration, and if you're in equilibrium, there is no acceleration. So the sum of the forces will be equal to 0. So when we're looking at things, we want to do a free body diagram. Also known as an FBD. All problems that you'll see from now on should be accompanied by a free body diagram. In chapter 2, it was necessary since we basically just had forces in different directions, but now we're actually going to be dealing with like a ball that has forces acting on it and things like that. So it's necessary that, you know, from chapter 3 on, you need to be having free body diagrams. So if we're looking at springs, a spring is denoted like that, where there's a force on the end of the spring. And this length of the spring is called L. Then we have an LO, and then a positive S. So where LO is the spring's natural state, and then you pull it down for plus S. So you've displaced it even more to L. So for spring, the force is equal to Ks, where K is a spring constant, and it's in units of newtons per meter or pound per foot. And S is equal to L minus LO, the deformed distance measured from its unloaded position LO. So if S is positive, then F pulls on the spring. And if S is negative, then F pushes on the spring. So for cables and pulleys, that's another thing that you'll see very often in statics. And for them, you have to make a key assumption. And that assumption is that all cables or cords will be assumed to have negligible weight and they cannot stretch. Or cords will be assumed to have negligible weight and they cannot stretch. This denotes like a ceiling or a wall, basically a fixed surface is what it denotes. So if we had a cable like this over a pulley, we have tension T and tension T, but this one would act at angle theta. So for any angle theta, the cable is subjected to a constant tension T throughout its length. So the procedure for our free body diagram is as follows. You want to draw your outline shape. And then identify and label all forces acting on the object. So we have our surface, and we've got a wheel. The weight would act through the center of the object. And then the force from the ground would act up. Just like that. So after we have our free body diagram, then we're going to use our coplanar force systems. So that means only two directions. So the sum of the forces is equal to 0. And so the sum of the forces in the x direction is equal to 0, and the sum of the forces in the y direction is equal to 0. Okay. So let's look at our procedure for analysis. First, you're going to do the FBD. You're going to establish the x and y axes. And a logical orientation. You're going to label all forces. Acting on the object. So a note, if you don't know the direction of the force, it can be assumed while drawing the free body diagram. If you don't know the direction of the force, it can be assumed while drawing the free body diagram. Okay, so after you got your free body diagram, you want to use your equations of equilibrium. You want to apply the equations of equilibrium. So your sum of your forces in your x direction is going to be equal to 0, and the sum of your forces in the y direction is going to be equal to 0. Components are positive if they act along the positive axis. Are positive if acting along a positive axis. Components are negative if they act along a negative axis. Apply your spring forces if applicable. F is equal to KS. So, since the magnitude of a force is always a positive quantity, then if the solution of a force yields a negative result, it indicates that the direction is reverse of what is shown on the free body diagram. Right, so if you get that your force that you're solving for is the magnitude is negative 200, it means that it's actually positive 200, but acting in the direction opposite of what you show in your free body diagram. So that's all you have to do. And you can solve whatever the equation is asking for after you get your free body diagram and your equations of equilibrium. And this can also be applied to three-dimensional force systems. So, sum of your forces, sum of your forces is equal to 0, so that the sum in the x direction is equal to 0, the sum in the y direction is equal to 0, and the sum in the z direction is equal to 0. So if the geometry is complicated in 3 dimensions, then write out each force as a Cartesian vector. So it's much easier if you do force F is equal to Fxi plus Fyj plus Fzk. And then you set all the I, J, and K components equal to 0. And that's really what you'll see me doing in most of these examples. I find it much easier to solve the equation once you put it in Cartesian vectors.